So yeah, I'm going to start with a brief background on residential natural gas consumption and the usage of these appliances and how that makes up the residential natural gas sector. As many of you know, the gas pipeline does not end with the customer's gas meter, but continues beyond the meter to one or more appliances in the home. Relatively less research has been done looking at these emissions of methane from within the residential homes. A typical home can contain, one or many appliances such as stoves, water heaters, furnaces, fireplaces, etc. Each with the potential to emit some methane through incomplete combustion or leaky pipes. There we go. All right. So over the last 10 years, the U.S. has consumed about 27.3 trillion cubic feet of natural gas annually. The residential sector accounts for about 17% of that total consumption, about half of the consumption from the industrial and electric power industries separately. Commercial natural gas uses a little less than residential, and transportation makes up a small part of the total, mostly from liquefied natural gas. All right, so focusing on residential emissions, in total, residences use about 4.6 trillion cubic feet natural gas per year, about 10% of the total production of natural gas in the US today. By far, the biggest user of natural gas in residential homes is space heating, taking up about almost 3/4 of that usage, which includes anything from whole house furnaces, wall heaters, fireplaces. And the second biggest user is water heating, including both storage and tankless water heaters, which we'll cover in part of today's presentation. In warmer climates, such as California, the amount of gas used for space heating and water heating is more equal. Cooking appliances makes up just 3% of the total gas consumed in residences. And this includes cooktops, ovens, outdoor natural gas grills, and the appliances that make up that other 1% include things like pool heaters, hot tub heaters, clothes dryers. So when comparing the total gas used with the number of appliances in residences, we see as seen on the plot on the right there, you can see the distribution is much more even. Stoves and the appliances in that other 16% section just use much less gas than space heating and water heating. In total, there are nearly 190 million gas appliances across almost 70 million residences in the US. This comes out to approximately 2.8 gas appliances in each home with natural gas. So think water heating, space heating, and cooking. So in this work, we contributed new data on methane emissions from residential appliances, which have been relatively understudied to date. The EPA currently offers no estimate for residential home leakage in their greenhouse gas emission inventory, but they've recently stated that they will include these estimates in future inventories, which is great. In the following two sections, we'll talk about the direct measurements that we made to measure emissions from water heaters and stoves. So first we'll describe methane emissions from water heaters, looking at the difference between storage and tankless water heaters. This work was published in ESNT in 2020. The storage water heaters shown on the left are the most common natural gas water heating appliance with about 56 million in homes in the US. Tankless water heaters shown on the right there are newer technology and most common in Europe and Asia, but they are becoming more popular in the US. Unlike storage water heaters, the tankless water heaters have a high-powered burner that can heat water on demand. The new technology is appealing to homeowners mainly because the promise of endless hot water and energy saving as they are more efficient. So for this study, we set out to quantify methane emissions from water heating during each phase of operation. using a direct capture method, which we'll describe in more detail here. So the direct capture method that we used involved collecting all the emissions directly from the exhaust of the appliance, whether that was on the appliance itself, like you can see on the left with the tankless water heater, or from the vent stack on the roof, as you can see on the left with the storage water heater. We use a Minneapolis Duct Blaster to capture the emissions from the appliance. The Duct Blaster is typically used to test the leakage in a ducting system of a building by pressurizing or depressurizing the ducting system. But it also functions as a fan that can produce an airflow up to 1,000 cubic feet per minute, and it reports that airflow. So as the water heater was used, methane and CO2 and other combustion products were emitted from the exhaust and captured in the fan, which was then diluted with ambient air. Because we know the flow rate of the air through the fan, and we measured the concentration of the dilution air, which we also called background, we were able to calculate the total emissions from the water heaters. So for these measurements, we used a Picarro cavity ring down spectrometer to measure the total concentrations of methane and CO2 from the appliance. You can kind of see that in the red wagon there with the pump sitting on top of it. So we used that to wheel over to people's homes, and we kept it powered off of a couple large marine batteries. So this plot shows a typical concentration profile that was produced from the Picarro during our measurements of the water heaters. A background measurement was taken away from the house and shown by the horizontal dotted line there. Emission rates while the water heater was off were measured first and are a function of the fan speed and some extra methane released over the background. After the water heater was turned on, a new on emission, so that's the steady state on, let's see, a new on emission was then calculated, typically different from the off emission. A pulse of methane was released when the water heater was turned on or off, and the total amount of methane was then calculated by integration of the methane profile given to us by the Picarro. So now Eric is going to walk us through some of the results that we got from these measurements of water heaters.
So I'm going to talk through the results here for the water heaters. So we calculated the total emissions, as Colin just mentioned, from each period of the water heater operation while it was off, while it was running, while off, and the total of methane that was emitted while turning on and off, which we call the on-off pulses. So in this plot, the y-axis is the rate of emissions in grams per hour. The solid line denotes the median measurement, and the dotted red line represents the mean. And in total, we found that the emissions from tankless water heaters while on were much higher than storage water heaters. Storage water heaters emitted nearly no methane while on, and in some cases were methane consumers. Tankless water heaters, on the other hand, emitted nearly 1.5 grams of methane per hour. While off, seen on the right, storage water heaters emitted more methane than tankless water heaters, likely due to the incomplete combustion of the pilot light in these units compared with the electronic ignition from the tankless water heaters. There are electric ignition storage water heaters, but they're, so at least a sample set that we had in California, they weren't as prevalent as the pilot lights. Pilot lights were still by far the dominant source of ignition in storage water heaters. And then the pulses we can see here from the tankless water heaters are quite a lot higher than the storage water heaters, especially while turning on. And then we found that the tankless water heaters, and then the off pulses are also a bit higher for the tankless water heaters compared to the storage water heaters. The interesting thing about the tankless water heaters is that we also collected data on how many times per day that these appliances turn on and off. And it can be expected that tankless water heaters, because they are triggered every time that hot water is requested, so anytime you turn your faucet on, it'll trigger the hot water heater to go through an entire cycle of turning on and off. So we collected data from 23 homes from each type of water heater for usage patterns, and we found that the total usage time per day, which can be seen here in the top plot, was comparable between storage and tankless water heaters. But the number of draws per day, as I just mentioned, is a lot higher for the tankless water heaters. They use about 10 times more frequently than a storage water heater per day. We also plotted the length for of each of the draws. So we can see here that in the x-axis, we see the length of time that the draw was emitted, and then the relative frequency of each draw is on the y-axis. So most draws for tankless water heaters are shorter than 1 minute, but for storage water heaters, the draws are typically much more than in 1 minute, which makes sense as well because the storage water heater is reheating the water inside the tank, but a tankless water heater is just on for as long as the hot water is on. So one of the implications of this is also looking at how behavior use can influence the demand for hot water from a tankless hot water heater. So here we see that we're going to plot the range of motion of a typical single faucet kitchen sink. So if you think of a kitchen sink that you have that, you can turn the handle to cold or hot, but it's not a two handle sink. So if you turn the handle to a certain percentage, we wanted to know how far did you have to turn it in order to trigger the hot water heater. So what we found here is that between 0% here representing all the way hot, 100% representing all the way cold, we found that you had to get to about 55% of the way, and then you would be triggering the cold, the hot water tank would not be triggered anymore. So if you have the handle exactly in the middle of the sink and turn it on all the way for the sinks that we tested, you would trigger the hot water heater. So the interesting implication here is that sometimes you may not even want hot water, and you turn your faucet on, and the hot water tank comes on, or the hot water heater comes on, and you don't even get any hot water from the sink, or you don't even want it in the first place if you turn it on for, say, 10 seconds to wash your hands. So we use these data, the two different data sets we collected here, the emissions data and the usage data, to create an estimate of total emissions attributed to water heating on a regional scale. So first, we took our emissions measurements from all the water heaters we studied, and we paired them with usage data from all the water heaters that we logged. And so we created pairings of every possible combination of emissions and usage data, and then we calculated the total annual emissions from each water heater using each set of usage data. So first, we looked at the total methane emissions per water heater, measured on the y-axis in grams of methane per year. Storage water heaters emitted slightly less than 1,500 grams of methane per year, with more than 96% of these emissions being attributed to the steady state off emissions. Tankless water heaters, on the other hand, emitted 72% more methane than storage water heaters under average operating conditions that we measured, and with about half of the emissions coming from the turning on and turning off phases of operation. The remaining methane emissions were nearly split between the steady state off and on periods. Next, we compared how these total emissions compared to the total carbon impact of these appliances, which is plotted on the plot here on the right, in terms of kilograms of carbon dioxide equivalents, using the global warming potential of 86 for methane over a 20-year time frame. And so we found here that the tankless water heaters are still better for a climate perspective due to their increased efficiency when you also incorporate the carbon dioxide emissions that would be associated with the higher efficient tankless water heaters. And also, just to put a plug here too, that our lab recently had another paper out yesterday in Environmental Research Letters led by graduate student Sam Abernathy and Rob's group, and found that if we want to keep with the goal of a 1.5 degrees Celsius warming world, we want to be using a global warming potential of at least 75 for methane, to using that target of 1.5 degrees Celsius. So that's one of the reasons also why we selected using the 20-year global warming potential instead of the 100-year for these comparisons. So from this study, we found that tankless water heaters overall emit more methane than storage water heaters, particularly while turning on and off. Total methane emissions can be further reduced most easily by eliminating the need for the water heater to turn on and off as much, specifically through behavioral changes by not triggering the hot water heater when the hot water isn't needed, or through design improvements such as a small storage tank to fill the small draws, such as hand washing. We also found that storage water heaters emit the most methane through steady state off emissions, which we believe to be in the incomplete combustion of the pilot light. Improvements here Oops, sorry about that. Improvements here can be, yeah, so improvements here can be made by switching storage water heaters to electronic ignition, which would eliminate the need for the pilot light altogether. Total methane emissions from water heaters, storage, and tankless combined was found to be 0.4% of the gas they use, which compounds upon all other sources of leakage in the natural gas supply and distribution chain. So now we'll switch gears and we'll talk about methane emissions from natural gas cooktops and ovens in single-family homes, which was recently published 2 weeks ago in ES&T. And Zutao is going to walk us through the methods for this part of the paper. Actually, I can present this slide here first, Zutao. So just this is just showing that cooking appliances, while they don't use very much gas of the total gas they use, they actually are a fair number of appliances. They do represent 23% of the total number of appliances. So even though the energy demand is a lot lower for them, there still is a good number of them in homes, and they represent a good piece of that pie.
Thanks, Erica. Okay. Yeah, I will show some details about our methods of our study and our experiment design. Yeah. So firstly, in total, we sampled 53 homes. Those homes are mostly in the Bay Area, in the Northern California, with a few sites from the Southern California, from the Los Angeles area. For all the 53 homes, we sampled the emissions from the cooktops. Additionally, we sampled for about 40 ovens from these homes for their methane emissions. And for we sampled logs from 32 cooktops and 24 ovens. So we used a chamber-based method to do our measurement. So briefly, we used some plastics to enclose the kitchen to make a room chamber. And besides that, we put fans inside the chamber, so to make sure the air inside and the gases inside the chamber was well mixed. But also we carefully select the position of the fans so do not disturb the combustion flames. Next, please. Yeah, here's just another example of kitchen closure. So depending on the standing of the house and the kitchen, we just figure out the best way to enclose the kitchen to make a room chamber. So we use the same analyzer as we did for the water heater to measure the concentration of methane, ethane, and carbon dioxide. Additionally, for the subset of houses, we use 2 analyzers to measure the concentration of nitrogen monoxide and the nitrogen dioxide. So the air was pumped through the hoses to the analyzer, and the hoses was put in the central area of the room chamber. And we measured the volume of the chamber using ethane injection. So we injected an ethane with a low volume to the chamber, and we observed that the change of the total concentration and used that to compute the total volume of the chamber, which has been shown to agree well with our measurements and using tapes. So we did that experiment. And we also observed the decay of the ethane over time, and used that to tell us the air tightness of the chamber. And then later on, we can use this decay rate to calibrate the concentrations of other gases. We measured the emission from various phases. And here is an example of the concentration profile of cooktop emissions. We first measured the SS off. We got this, it's called a steady state off from the stove as a home unit, because we cannot separate the off emission from different components. We then turn on burner on, which will usually produce an outpost of emission like the water heater. And then we let it burn on for a few minutes and with the pot of water on it to heating it up, like kind of simulated the actual cooking. In this stage, it will be release methane, carbon dioxide, and the logs. After that, we turn it off, and which will usually produce another post emission of methane, but not, of course, not carbon dioxide and the logs. So for the for the ovens, we also observed various emissions from various phase too. We usually first set it to a preset temperatures like 350 Fahrenheit. It takes about 10 to 15 minutes for the oven to preheat to its reset temperature. We call this the preheating phase. In this stage, we observed all the emissions for the three major gases we are interested in, and especially when it turns on, there's kind of also a post of methane. And when the oven was off, we observe a post emission of methane, but not for the carbon dioxide and the nitrogen monoxide and dioxide. After that, to keep the temperature, the oven usually will repeatedly turn on and off. We call this the cycling stage. And when it is on, it releases methane, carbon dioxide, and the logs. But when it was off, it usually only produces an post of methane. So this cycling keeps going on until we turn it off. With that, I think I turn over to Erica for the results.
Yeah, thank you, Zutao. So yeah, I'll walk through the results now, what we found for the stove work. So first, we're just going to walk through like we did with the water heaters, through different phases of operation and the emissions that we found from them. So this first plot looks at the emissions from steady state off that we collected. And in this plot, each black dot represents a single measurement from the stove, which we took about 2 to 5 times at every stove we measured for steady state off emissions. And then we grouped the black dots into bins, which are seen on the x-axis with labeled ID for each of the 53 individual stoves that we visited. And on the left is a summary box plot, which shows the median and the interquartile ranges, and then the red star represents the mean for each of the 53 stoves. We found that the average emissions from steady state off were 58 milligrams of methane per hour. Emissions are also long tail distributed, which means that a small number of stoves are responsible for most of the emissions. And this is seen also that you can see that the y-axis here is on a log scale, so that it's even more a long tail than what you might visually see. We found that the highest 9 emitting stoves had no individual measurements of steady state off, less than the overall average, which suggests that it's these few stoves that should be the most concerned about for these off emissions from stoves. Meanwhile, we found that steady state on emissions were much more variable and overall were more than 4 times higher than the emissions while off. We found that emissions while on were 259 milligrams of methane per hour, and this was only from the cooktop burners. Separately, we measured ovens, which emitted about over 600 milligrams per hour while preheating, and even more than that while they were on. Once they reached that set temperature, Zutao mentioned that they were constantly cycling so that we would continue to see emissions while they were on and maintaining temperature. And then we also measured the pulses of the methane, which Zutao described in the methods. And we see that they contribute overall to the emissions from the stove, and that they were emissions were highly dependent on the burner and then the specific lighting conditions, as some older burners had trouble lighting and did not light right away, which you can see on the higher burners on the left. We found that the Overall, the emissions average to be about 46 milligrams for on-off pulses for an individual ignition and extinguishment cycle. And this corresponds to about 10 minutes of steady state on concentrations emissions, which means that lighting the burner for the stove will add about the same amount of methane as if you had left the burner on for about 10 minutes. So just like the water heaters, we estimated the total emissions of the stoves by combining our emissions data set with usage data set, which we got from researchers at LBNL. This data set also contains information about the number of times per day a stove and oven gets used and for how long it is used. Annual emission estimates were calculated for every pairing of stove and methane data and usage data available to create an average annual emission and confidence intervals for that estimate. So using all these data, we found that the methane emissions from stoves total nearly 30 gigograms of methane per year. Total methane emissions from water heaters from the previous study were about 3 times higher, but you'll recall that they use nearly 10 times the amount of gas as a typical usage scenario for their heating purposes. Broken down into different categories of usage, we found that the emissions from steady state off were responsible for about 3/4 of the methane they emitted. The remaining emissions were broken down into emissions from the oven and steady state on from the cooktop, and a small amount from the on-off pulses. When compared together, we found that methane emissions from the stoves increased the climate impact of the stoves by about 39%, using the global warming potential of 86 for the 20-year time scale. And this is mainly because of the relatively high emissions of leak gas of methane during the incomplete combustion and also while the stove is off. So we found that the total annual carbon dioxide emissions from stoves, just the amount of CO2 you'd expect to get just from burning the gas, is 6.2 million metric tons of carbon dioxide per year. And then the methane emissions added on to that is 2.4 billion metric tons of CO2 equivalents every year. So in addition to methane, we also measured the total emissions of nitrogen oxides, as Zutao mentioned, or NOx from the stoves. We care about NOx, which is the combination of nitric oxide, which is NO, and nitrogen dioxide, NO2, because NO2 is a respiratory health damaging air pollutant. NO is oxidized into NO2 through reactions through sunlight and ozone. Naturally, NOx is formed primarily through lightning strikes. The Earth is struck by lightning more than 40 times per second. It's also emitted from man-made sources, such as combustion from vehicles, either in cars, trucks, power generation, or as we find here, from stationary combustion from natural gas appliances in homes. And it's formed from the combustion because of the high temperatures in the flame and excess oxygen in the combustion. The plot on the left here shows that NOx is formed readily at temperatures over 2800 Fahrenheit, which is a temperature which can be reached by a typical kitchen stove. And the plot on the right shows that excess oxygen, around 5 to 7%, is most optimal for NOx formation. So we aim to quantify the total NOx emissions from a stove alongside our methane measurements. We found that NOx from stoves is particularly important because it is emitted directly into your house, unlike the other gas appliances, which are typically outside your house or directly vented outside. When the stove is used, the ventilation hood almost never comes on automatically and needs to be turned on by the user, which dramatically would help clear out the NOx from the kitchen. The EPA has set an exposure limit of 100 parts per billion over 1 hour period for NO2 before it is considered unhealthy for outdoor standards. Well, there are no indoor air quality standards for NO2. By quantifying emissions from the stove, these data will help legislators determine appropriate ventilation hood speeds in order to keep NO2 concentrations in acceptable range. And these are conversations that are currently happening in California right now. Since NOx is formed more readily at higher temperature, it makes sense that the NOx emission rates are also correlated with the total amount of gas burned, which is what we found. Here we show that the NOx emissions on the y-axis of the natural gas flow rate on the x-axis. We found that there does indeed exist a correlation between NOx and gas flow. And so this has implications for determining how much NOx is emitted from a stove, which means that the more burners you use or the higher the temperature is of the burners, or if you use a bigger burner, it'll all produce more NOx over time, at the same amount of time than using a smaller or fewer burners would. So because we found that the NOx emissions from natural gas flow rates were correlated, we reported the total NOx emissions in terms of the mass of NOx emitted per unit energy. And here we measured the joules of the output from the stove as shown on the y-axis. So we split the measurements up into cooktops on low, medium, and high, and ovens during the preheat and cycling, as well as during turning the broil burner on separately from the oven. And there were a few stoves which also had a griddle element as part of their cooktop, just like a griddle that you could use as a grill, and it was in substitution of a burner. We found that NOx emissions range from 15 to 28 nanograms per joule, with an average of 21.7 overall. And to put this in perspective, the average light-duty automobile, which typically emits about 55 nanograms per joule, even though they burn a lot more energy. It is a comparable emission rate. I mean, stoves are about half of the automobiles, but just to put that in perspective. But remember that stoves emit directly into your house. So we said that the 1 hour exposure limit of NO2 is 100 parts per billion. And this could be reached by your stove with higher concentrations achieved in smaller kitchens, especially those that have poor ventilation and higher emission rates from the stove, which would be achieved if you used more or stronger burners. So one of the best things the user can do to reduce exposure is turn on your exhaust hood anytime that you are using your stove. And we found that about 1/3 to 1/4 of typical gas stove users don't turn their hoods on when they're cooking with gas. And this plot shows concentrations from an oven that we measured. These are actual concentrations from an oven that we measured. And we didn't use the plastic partitions in this particular house like Zutao showed earlier. This house was compatible enough that we could just use the kitchen and living room themselves as their own chamber. So the concentrations here are not influenced by a smaller room size. But although we kept the exhaust hood off while taking the measurements, you can see that just by turning the oven on, it's possible to exceed that 100 parts per billion standard for NO2 just by using the oven in this space. So just to summarize a few of our key findings from stoves, we found that total methane emissions were 28.1 gigagrams of methane per year. And more importantly, this equates to about 0.8 to 1.3% of the gas they used. These emissions increased the climate impact of stoves by about 39%. And we found that 76% of methane emissions from stoves were emitted while the stoves were off. And these emissions from other phases of the gas stoves were long-tailed, highlighting the future need to identify the highest emitters from these appliances. And NOx emissions were 15 to 28 nanograms per joule, or about 1.6 to 2.9 grams per therm, which is enough to exceed the NO2 exposure limit set by using the stove, and which is particularly can be done in smaller kitchens than those that have less ventilation. So just wanted to give a quick summary of the findings and putting our results in context before we head off to question and answers. So first, we just wanted to show that the total emissions and how they compare with other appliances and other work that's been done in this space. So we found that from our work for water heaters, we found that the total amount of methane emitted was 82 gigagrams of methane per year, which is about the same as emissions as 1.5 million cars on the road when using the 20-year global warming potential for methane. And meanwhile, stoves were emitted about 30 gigagrams of methane per year, which is about 500,000 cars. We're still measuring furnaces ourselves, but another study by Zach Marin and Paul Francisco found that furnaces and boilers tend to emit about 9 gigagrams of methane per year, which is about 170,000 cars. Although we need to spend some more time looking at the off measurements from the furnaces and boilers. So in terms of total gas used, we remember that the furnaces use the most gas, then water heaters, then cooking. And all of this totals about 4.6 trillion cubic feet per year. And these are the total emissions from that gas used at the appliances themselves. When using all these emissions rates together, we find that the total emissions per gas used is about 2.2% of the gas that they use. Although we do need to refine some of these estimates, particularly with some of the other appliances that haven't been measured yet. So our estimates can help fill in some of the gaps from the EPA inventory of greenhouse gas emissions. As we mentioned, our estimates of water heaters and stoves combined with other estimates of furnace suggest that about 0.2% of the gas entering the homes might be leaked as unburned methane. We found that more than this is emitted from water heaters, which we found to be about 0.4% of all gas used, and stoves, which we found to be between 0.8 to 1.3%. And since methane is such a strong greenhouse gas, it's important to know that, you know, these may seem like small numbers, but if just 3% leaks from the components, all the components of the supply and distribution chain, it would double the greenhouse gas impact of the burning of this gas over the next 20 years. So now I just want to give a few ideas for things that we're working on and ideas for future research. So one of the things that California has thrown out too is there's a few RFPs out there right now. One is looking at trying to get a larger sample size, focusing on multifamily homes in economically disadvantaged communities. And it's an RFP called Improved Characterization of Methane Emissions from California's Residential Sector. Another one is looking at better understanding the health impacts of NO2 emissions, specifically from gas stoves, which is also in progress with the CEC. There's a randomized trial study to investigate the impact of gas stove interventions on children with asthma, which is super interesting. Some other things that a lot of folks have mentioned too is just looking at propane appliances and electric appliances and seeing how, specifically with propane appliances, what the carbon impact is of burning the gas, and also the health impact of how much NOx is produced from propane appliances. I'm not sure that anybody's measured NOx emissions from propane appliances directly. And there are 10 million users of propane in the US, so it's not a small amount, especially those in the rural communities. Looking at other pollutants from the stove, like formaldehyde, carbon monoxide, particulate matter, and emissions of estimates from other appliances such as fireplaces, furnaces, and clothes dryers are something else that hopefully we'll get some more measurements of those, especially with the CEC grant. And so I'll end there, and thank you very much for coming today, and we'll be delighted to take any questions.